So we've already done this problem twice, but that's not enough. We're going to do it 3 times. And so we're seeing lots of different ways to solve these problems. It's useful because different methods are quicker for different problems. So it's useful to have it to see them all. And each way of doing it gives you a different idea about what the moment is and how it works and how it all fits together and relates to the point of rotation and the object and so on. So it's quite useful to be aware of all these different methods. And so what we've done so far is we made a scale drawing to figure out the lever arm, and then we used that to calculate the moment. We've also used trig to figure out that lever arm and then figure out the moment. This time we're going to have a look at resolve the force into its x and y components and use that to figure out the moments. Let's just move this into place. What I might do is I might just draw the x and y components on this, but I might just draw it again separately just for our trig, just so that you can see where we're going. So we're going to have an x component this direction, and I might just take y positive downwards this time just to keep everything positive. So we'll have a y component this way. Okay, and I'm drawing those on the correct point of application. So I'm thinking about moving it nose to tail. So I'm imagining we just get two vectors that go nose to tail to go the same way. But all I'm drawing is the force at the correct point of application. So these forces are both being applied here. This gets even more important when you're doing moments. You don't want to start drawing forces in the wrong place because you might accidentally use the wrong lever arm if you do that. So the forces are all applied to the same point. This is Fy. So I might just redraw the force, not the whole thing. We've already done, so what was it, 30 degrees. Just do it a bit bigger so we can see what's going on. X component, like so. I'm just going to move this up a bit. Y component is here. We could have done it nose to tail. So we could have drawn it over here just to imagine adding them. We're not drawing it there in the end because we want to have the right point of application. And we know that this in here is 30 degrees. And we know the hypotenuse is 20 kilonewtons. We know our right angle is here. Therefore, that's our hypotenuse. And we want to calculate opposite the angle and adjacent to the angle. And adjacent, this is really the same as Fy, this is the same as Fx, and just so that people know what we're doing in terms of signs and so on, I'm just going to take my axes like so, just reverse the y-axis just so that all the force components are positive. So let's try and figure out what the x component is first. So it's adjacent, we've got hypotenuse, this is the angle, A and H, so k cos. So cos 30 degrees equals, let's just write it out, adjacent over hypotenuse, which equals adjacent is Fx over hypotenuse is 20 kilonewtons. Don't write your units. So Fx times both sides, Fx is equal to 20 times cos 30 degrees, which is equal to 20 times 17.32. Now if I'd been smart here, I would have thought to myself that that x component, the line of action of that x component is going to go straight through the point of rotation, and so I don't really need to calculate that. but we'll just write it out in full so that anyone reading these calculations without looking at the video knows what's going on. So d of x, so your lever arm for x, so the lever arm for the x component is equal to 0, therefore the moment due to the x component is also equal to 0 kilonewton meters. Not the case for the y component though. The y component's in this direction, and so the lever arm is a line from the point of rotation at right angles to the line of action of the force, so it's just this distance here. So let's figure out Fy now. So Fy opposite, we've got hypotenuse, so it's sine. So sine 30 degrees is equal to opposite over hypotenuse. So therefore Fy is equal to 20 sine 30 degrees. I've done that enough times now that we know that's going to be 10. Sine 30 is just a half, so that's going to be 10. What are we in kilonewtons? 10 kilonewtons. So the moment that arises from the y component of the force, we've already got d, so that's all good, is equal to Fy times dy. Now, let's think about the rotation for this. So if we pull this down here, it's wanting to rotate. Let's just draw it. It wants to rotate this way due to the y component. Clockwise, negative, and so we need to just stick a negative in front of that. So my is equal to negative 10 times 3, which is equal to minus 30. Our force was in kilonewtons, our distance was in meters, so minus 30 kilonewton meters, which makes me realize, I hope you spotted it, moment of force about A equals minus 30 kilonewton meters, which has made me realize that I made a mistake earlier because I forgot to think about the direction of the moment. And so when we did these problems, we were saying that's 30 kilonewton meters, but it's not. The direction of rotation, it wants to rotate this way because of that force. That's clockwise, thumb down if you're using the right hand rule. So all of this should be negative. So that should have been negative 30 kilonewton meters. This here should have been negative, should have been negative, should have been negative. And so this answer should have been negative. Which is one of the reasons why you always try and do a check on your answers to go back. If you've made any mistakes, you'll find that mistake when you do your check and correct it. In this case, the direction is not critical because we're not going on to use it anywhere else, but I would probably still mark it wrong if I was marking your test, so don't do as I do as I say. Make sure you check your results and be especially careful with negatives for moments plus or negative.